Okay, so welcome home group. This is NS for today. We're doing electric circuits and we're on page 113. I'm going to present your heading and what you need to do. We've already watched the video that I'm going to send, so we know how to draw an electric circuit. We're looking at unit 12.2, which is circuit diagrams, and we're looking at activity 12.2.1. Right, activity 12.2.1 asks us to draw each of them in your science book in symbols. So you're not going to draw the battery and the little light bulb. You're going to draw the symbol for the battery, just as the guy in the video did. So it'll look like this. Activity 12.2.1, number 1, looks like that. Okay, so it's asking us to draw the batteries, which are those cells, which you can see are those lines that I've drawn. Then you have the switch. My switch is open or closed? Closed. And then your light bulb. So exactly as it shows in your textbook, that very first one. So I've drawn the very first one at the bottom of page 113. That one. So I've drawn that one. You need to draw all 3 of them. So you'll have to draw all 3 of these. I've drawn the first one for you. So with a ruler and a pencil, you'll have to draw that. Any questions about how to draw a circuit diagram? Everybody okay with, you need a ruler, you need to do it in pencil, you know how a cell looks, a battery, you know how a switch looks, you know how a light bulb looks? Yes. Okay. So you're going to draw this, and if you turn the page 114 asks you to draw 2 more for number 2, but it doesn't give you a picture, it tells you what to draw. So you'll have to imagine what they are explaining. A circuit, I'm reading 2A, a circuit consisting of a cell, a switch, and a lamp. A cell, a switch, and a lamp. So it doesn't tell you where they need to be, it just tells you in words what you need to draw. 2B, a circuit consisting of a cell, a switch, and 2 lamps. And then it says all in series. What do you think that means? You get parallel and you get series. What do you think that the 2 of them mean? What is parallel lines? Yes.
Lines are opposite each other.
Give it to me a little bit more information there.
It's lines that are opposite each other, but they are going in the same direction. Stay in the same direction. Lines that never meet.
Yes. Lines that will never meet, lines that are next to each other, lines going in the same direction. We're all getting to the same point here. So if I have, let's say these two pins are parallel to each other. So they're next to each other, but they're not touching each other. They're just next to each other like that. Okay, so that would be parallel. So if you had 2 cells that were parallel, the one would be on top of the other one, like that, and you would have circuit lines from both of them. But in series, it means that they're next to each other. So these 2 cells on the board, the long line, short line, long line, short line, those are in series. They're next to each other. Okay. If I had, if I had 2 cells like that, they would be parallel to each other. So they're 2 different lines there. But if it's next to each other, like that, it's in series. If I have 2 lamps parallel, be like that. So they're not on the same line, but they're in series, they'll be next to each other. Okay. And then number 3 says, describe these circuits in words. So now you have to write it in words from the diagram shown below. So A, you need to put it into words. B, you need to put it into words. They have an example at number 2 because they've already written it in words for you. Now you just have to describe the ones in number 3. Got it? Right, moving on. I'm not going to let you do the whole activity now. I'm going to go through everything and we'll come back to that. I'm on page 116, 116. Sorry, I don't know what's wrong with my voice. I'm on page 116 and it tells us that there's a summary, so summing up a simple circuit. I'm going to go through this quickly because you guys have read it already. You should have knowledge of this. I'm basically scanning through it. So an electric circuit is a system for transferring energy. Transferring meaning? Transferring?
Giving energy from one place to another.
So giving energy from one place to another. A simple circuit always has the following components: a source of energy, such as a cell or a battery. What is the difference between a cell and a battery? Not quite. What's the difference between a cell and a battery? If you look at 112, page 112 at your table, what do you notice? What's the difference between a cell and a battery?
A cell is one.
Okay, a cell is 1 unit of electricity there. And as soon as you add more, it becomes a battery. Okay, so 1 short line, long line is a cell, but 2 long line, short line, long line, short line, that becomes a battery. Even if you add a third one and a fourth one and a fifth one, 100 ones, it's a battery. Okay. Conducting material such as electric wires to carry the electric circuit. So the lines we draw is the wiring, the conducting material. If I look at this laptop, so the laptop has a cable, plugs into the wall, and I can charge my laptop's battery. So it has a cable to get electricity. That cable, if I had to draw it as an electric circuit, would be the line, that rectangle that I'm drawing. That's what that line represents, the physical cable that takes the charge, or that transfers the energy. And then 1 or more devices such as a light bulb, a buzzer, or a motor for changing electricity into useful output, such as light, sound, or movement. So if I put a fan on, it takes that electricity and turns it into movement. If I put the sound on the laptop, it makes sound. Or the last one was light. Put on the light, it's an easy one. A circuit is a complete unbroken pathway for electricity from source through the conductor and back to the source again. So what did we say was the conductor? The wire. Thank you. Someone's awake. And I'm going to skip the next one. And then it says a switch can be added to break or complete the circuit pathway. As we said, if you swap out the light bulb and the switch, then what's the point of the switch? You can't put anything on or off then. There's no point in having a switch. The light would just be on all the time. So that switch is there so that you don't have constant energy transfer. If I had to plug my laptop in and the switch wouldn't turn off again, then my laptop would keep charging and keep charging. It wouldn't be good for the battery in the laptop to have that constant energy on it. If you think about your house and that electricity that comes from the always struggle with that word, municipality. There in your house, there's light switches, there's switches for the microwave, the fridge. You can put all of those things on and off but the electricity coming into your house is constant. No one's putting that off unless there's load shedding. So that comes in all the time. Either in your garage or your kitchen, you'd find a circuit breaker. So a little box with switches on it. And you could put the geyser off. Let's say you guys are going away for a long time. You put the geyser off so you don't waste electricity that way. Or maybe your mom puts the oven off when she's not using it so that your little brother or sister can't put it on. All of those switches on the circuit board is there to be able to put that electricity on or off. If the mains go off, the main switch, that means that you've now put off the electricity coming from the municipality. Sometimes it just trips. You might have heard your parents, oh, the electricity's tripped. That means that switch has just gone off. You can go and put it back on, and the electricity will come back on, unless obviously it's load shedding. So you need a switch to be able to put that electricity flow on or off. And that's it. So that's just a quick little summary. Then on the same page, it says question time. You're going to answer these questions in your book. So after you've done 12.2.1, you're going to answer these questions. You can just write page 116, question time. Number 1, what is the most common form of wasted energy in electrical appliances? 2, what form or forms of useful energy is produced in each of the following devices? And 3, why do we use circuit symbol diagrams instead of pictures of the components? Okay, now, if you're wondering where am I going to find the answers for number 1 and 2, remember that on page 110, I did that summary with you. That's where you would answer questions 1 and 2 from. So you wrote down a summary from the board, and they spoke about waste energy. Got it. Right, moving on. Conductors. What is a conductor? It's not a train conductor, but what is it? Zara, tell us, what is a conductor? You guys should have read this. Yes, so it's the wires or the cable that would transfer that electricity. Okay, what would this conductor be made of normally? Copper. Copper conducts electricity quite well. What else would conduct electricity? Yes. Your hand went up. It was a quick up and down. Anybody else? What else would conduct electricity? What other things?
Porcelain?
No. Not porcelain. What else conducts electricity? Whoa. Did we not read? What else would conduct electricity? Different metals. Aluminium, silver, gold. All of those conduct electricity. Okay, a lot of people who work with electricity, so they're electricians or they work at the power station or wherever, wouldn't have a gold or silver wedding band. They would have titanium or something else that wouldn't conduct electricity, because if they do shock, then that would burn. So that the electricity that might touch the ring could burn the person's finger. Okay, or they would wear rubber gloves, safety gloves, rubber-soled shoes. If they do shock, then that would stop the electricity flowing completely through them. Okay, so a conductor conducts electricity. It transfers that electricity through it. Most metals conduct electricity. Right, so in that little picture, 13.1.1, you'll see there's plastic insulation, and then the copper wire. Why is there plastic around it? What's the point of that little red plastic in that picture? In a way, Diego. Sorry, it's the picture 13.1.1.
Right, so have an electrical wire. No, on top of this one. 117.
But I'm not quite following your question. Okay. Anybody else? Why is there this plastic thing around it? Tristan?
So we call electric other things like wood and things from fires or
Want to find a friend, Jad?
To keep people from shocking when they touch it.
Yeah. If there was no plastic around this thing, I know you had it right, and I nodded at you. If there was no plastic around this and you just had the copper wire, then if I touched it, I would shock because it's plugged in. It's in an electricity point. So I would be shocking now. The same with the board cable, the cell phone charger, the cable going from the kettle to the plug. If there was no insulation around it, then we would all be shocking. It would be a shocking experience. We can't then plug anything in. What are we going to touch? We can't touch the wire. Thank you for laughing at my terrible joke there. It wouldn't work. We wouldn't be able to do anything. So this insulation around the copper wire protects us and it protects the wire. Now, I'm sure you've heard on the news that there's been, every now and then there's cable theft. And what that actually means is that someone has gone and cut the electrical wiring from the trains or a building somewhere, and they've taken all of that. It's a huge pile of wire, and then they go and burn this because plastic burns at a lower temperature than copper. So what they do is they're melting the plastic off the copper, and they're left with just the copper, and that's valuable. That they can take to a scrapyard and sell. They make money out of that. So that's why people do that. But it's very dangerous because if you've cut it and there's still electrical flow to it and you touch that copper, you're obviously going to shock. And people have died because they tried to steal wires. I don't know if sometimes you see like a huge puff of black smoke coming from an area and you think, oh, shame, maybe someone had a bit of a fire incident, but it could be people that they're burning copper wire. Sometimes the very, very old TVs, so no flat screen TVs, but those big box TVs had a copper ring in it, and people would buy that, smash it, or not buy it, steal it, and smash it, and then take out the copper and sell that. So it's a valuable thing to sell, and that's why it gets stolen. But that plastic covering needs to be taken off first. You can't just arrive there with this reel of cable. That needs to come off. So the plastic is taken off. You get wire strippers, which is a like a little pliers that you take around the wire. It cuts the plastic and you take it off. I'm going to show you just now. I'll show you a video of how they take that off. So the plastic that we're talking about, if you look just underneath that picture, it says 4 with a little triangle around it, PELD, which is low density polyethylene. That is what it's made of. At the very bottom of page 117, it tells you about 2 core flex and 3 core flex. Okay, I'm not going to go into that, but just note there's 2 different types of wiring for different things. If I have my laptop cable, it doesn't take a lot of energy. It doesn't need a whole lot of electricity from the plug point. It's just charging. But if I put the oven on, or the microwave, or the kettle, it uses a lot of energy to heat up whatever's in it. So it would have a thicker cable. And that would be 3 core flex. Right, moving on. Insulators. We've spoken about what an insulator is. We get the plastic around the cables, but what else do we get that insulates? Why do we have insulators? It's quiet. Leila, why do we have insulators? Oh, I'm gonna run out of time. Yeah. No, yes, Ian.
So that the electricity flows
Okay, in a way, the electricity is meant to go in a certain way, but insulators protect people working on these pylons. So that picture there, that big steel structure is a pile-on. That's what it's called. And you see those little glass, like, I don't want rings around it, stops the electricity from making that whole metal structure electric. Okay, so the electric wiring going over that structure takes the electricity from this place to this place to this place. But that steel structure keeping it up out of the way of people can't suddenly be electrified. Because if you go and touch that thing, you're going to shock. So those porcelain or glass little, I don't even know, what do they call it? Let's just call them insulators. That stops the electricity from making that big structure electrical. So you can go and touch it. Don't go and touch it, but you could go and touch it. Don't go and play under the pylons, people. If you turn the page, there's some more examples. There's more examples of those. And then I quickly want to jump to page 122. So we're running out of time and I still need to hand out your test. Oh, then I want to go through the test. Anyway, so there's another summary, conductors and insulators. I'm not going to read through that. You should have read through this already. And you're going to do question time on page 123. Okay, so at the bottom of page 123, there's question time again. So I'm going to put this on the board of exactly what you need to do. Ta-da, this is why I take my mouse with me, but I've got. Okay, page 113, activity 12. It's supposed to be 2. Sorry, 12.2.1. Page 116, question time. Page 123, question time. So you need to do that for next time that we have NS. Are there any questions? I know I went through this quickly, but you guys have the knowledge. You were supposed to have read it. If you have any questions, you have time to ask. Always WhatsApp me or ask mom or dad. Yes, but we'll do a little bit more about it before we write a test about it. Sorry, hold on. Nothing, because it's there to protect you. Yeah, you'll shock. Okay, so for the home group, that's it for this lesson. Please go and watch the video that was sent last week about circuit diagrams and do the activities that are on your screen now. So I'm going to stop recording.
Thank you.